Hi everyone, welcome back to MATA02, the Magic of Numbers. Today we are going to be talking about what some people consider to be the most magical of numbers. We're going to be talking about prime numbers, which I'm sure you guys have heard about, but we're going to go through it in carefully and try to figure out what's really going on. And so, I could give you the definitions, I could give you the theorems, but that doesn't really get you the intuition of why these things are so magical and what's so cool about them. But before we get there, we have to talk a little bit about what we mean by mathematics, since in some ways this is at the heart of mathematics, and or at least number theory, which is a very big part of mathematics. So let's start with, my animation's broken. But let's start with the question, what is math? Now this is a super big question, but one of the nice things about having this class is that since I'm not trying to teach you a specific method, we can really talk about these big picture questions on occasion. So, is math just some game that's invented by humans? So we have a bunch of numbers, we write them down, it's some game that humans do that allows us to somehow model the world or whatever. Or does math exist somewhere in Platonic space? And we just discover it. So like, we didn't invent pi, we discovered it, clearly. Who would invent some number that's as weird as pi? Or, why not both? Maybe math is both discovered and invented. Or, who cares so long as it works? So there are all these questions of philosophy, but like, does anyone really care so long as it works? So let's see, what are people replying? So a lot of people are answering why not both, which is very often the safe answer, of course. But it turns out that all of these are answers that professional mathematicians believe. All of them, all four of these answers, actually. So some professional mathematicians believe that we are in the process of inventing math, and this is some human game, and that math is so powerful because we have invented it for the purpose of explaining the world. Some professional mathematicians believe that math just exists, and we're here as adventurers, discoverers, who are out in the Platonic wilderness, adventuring and discovering math like people, Antarctic explorers were discovering parts of the wilderness. And there are some people who believe a mix of the two, and I'm probably somewhere along those lines, where I believe that certain methods in mathematics are invented by humans, but that the properties we're finding are discovered. And there are a very reasonable number of professional mathematicians who just don't really care. Like, they do math, but you don't really need to know why you do math in order to do it. Plenty of us do things that we don't know why. And so this really is the sort of question that, well, some people would say it's invented, some people would say it's discovered, and if you think back to what we've been doing in this class, we've been largely inventing stuff, right? Like, that's sort of the language that I've talked about with like numbers and operations. We've been inventing negative numbers, we've been inventing multiplication, things like that. But today with prime numbers, it's going to be the case where we're really going to see a little bit more of the discovery aspect of mathematics. And there are weird facts about prime numbers that seem really odd to have just been invented by humans. Okay. So, let's give a quick review of things we did with addition and multiplication. So, we've obviously done these things before. Just a moment. So we've obviously done these things before, so just as a quick review, well, what is addition? Addition is just repeated counting. This is super easy. So if you had something like 3 plus 4, let's just say you're counting 3 boxes, and then you have another 4 boxes come along, and then you're counting another 4 times. So 1, 2, 3, 4, 5, 6, 7, and that's equal to 7. Oh, I need to be able to write. So that's equal to 7, and that's easy enough, and we've already been over that. Okay, so one way of inventing an operation is to repeat a process. Now, another way, so you can do this again. So multiplication isn't just repeated addition. So what is multiplication? Well, if you have 3 times 4, well, that's saying you're doing 3 plus 3 plus 3 plus 3, a total of 4 times, and that's equal to 12. Okay, and so we can keep on repeating if we want, but one of the things you might notice is that whenever you do these repeated additions or repeated multiplications, you have a couple properties that you might care about. So, for example, you have the commutative property, where x plus y is equal to y plus x. 1 plus 2 is equal to 2 plus 1. You also have the commutative property. 1 times 2 is equal to 2 times 1. And this is true for both addition and multiplication. We also have the associative property. So 1 plus 2 plus 3 is equal to 1 plus 2 plus 3. And 1 times 2 times 3 is equal to 1 times 2 times 3. And we also have the identity property, where there is some specific number for addition that's 0, and for multiplication that's 1, where if you combine that with your with any other number, you just get that other number back. And we added some other properties like the distributive property, which related together addition and multiplication, but these are the properties that are specific to just addition or specific to multiplication. And so you might notice, well, addition and multiplication look pretty similar, right? And in some ways that makes sense because they're both similar types of inventions. But when we start really digging deeper into addition and multiplication, you start seeing some differences between them. And that's what we're going to be doing today, and that's where the prime numbers come out of. They come out of the sort of inherent difference between addition and multiplication. So what do I mean by that? Well, let's try to build the natural numbers. So if we want to get all the whole numbers, we can get that by repeatedly adding 1. So we're basically using 1 as a building block. So 1 plus 1 is equal to 2. 1 plus 1 plus 1 is equal to 3, or you can think of this as 2 plus 1 is equal to 3. We also have like 1 plus 1 plus 1 plus 1 is equal to 4, or you can think of that as 3 plus 1 is equal to 4. Okay, and so on. So if you keep on going, you get 1, 2, 3, 4, 5, 6, 7, 8, and so on, all the way on to infinity, right? So this means that we can build up all of the counting numbers just by using the number 1 and repeatedly adding. But now, what happens for multiplication? So, well, what happens if you try multiplying by 1? Well, if you multiply by 1, you start with 1. Times 1 is equal to 1, times 1 is equal to 1, times 1 is equal to 1, and so on. So that doesn't work. So now if you try 2, well, 2 also doesn't work, because 2 times 2 is 4, times 2 is 8, times 2 is 16, so you never get a number like 13. You do the same for 3. 3 times 3 is 9, times 3 is 27, times 3 is 81, and so on. And so none of these sort of basic numbers seem to work for multiplication. You could try the negative numbers, you try 0 as well, but each time you can't construct all of the natural numbers just by multiplication, just by repeatedly multiplying a single number. So now, one thing you might think is, well, if you think of math as just entirely invented, well, maybe we can just invent a new number that works. So let's try that. So let's invent a new number. Let's call it alpha, that works as a building block, as a multiplicative building block. Okay, well, what would the properties of this number be? Well, you needed alpha to be equal to 1, and you need alpha squared to be equal to 2, and alpha cubed to be equal to 3, and alpha to the 4th to be equal to, not over, equal to 4, etc. But this is a problem, right? Because list lying implies that alpha is equal to 1, and list lying implies that alpha is equal to 2, which then implies that alpha is equal to 1, that implies that 1 is equal to 2. So this doesn't necessarily break everything, but it breaks most things. And so this is a problem. So this does not work. So we've just shown that we can't invent a new number that works for both, because if you were to try to invent a new number that works as the only multiplicative building block, well, you end up with you end up with a contradiction, because you end up with 1 is equal to 2, which we're assuming is, well, not true, or else all of math falls apart. Okay, well, you might be like, what if we allow ourselves to have more than just one building block? Maybe we can do that. So, like, clearly multiplication is different than addition. In addition, you only needed this one building block, the number 1. With multiplication, well, maybe you need some more building blocks. And let's just try to build a few numbers. So maybe we don't even try to build all the numbers. Let's just try to build numbers from 1 to 100. So I'm going to ask now, would the following work as multiplicative building blocks? So asking in chat again. So would the following work as multiplicative building blocks? If not, please give an example in chat of a number that fails. So by a number that fails, I mean a number you can't build from those numbers. So let's start with something easy. Well, we're trying to build a number from 1 to 100. What if I just give you a bunch of blocks labeled 1 to 100? Let me zero. Oh, I did zero it out. Okay. So does this work? And if you're answering no, it doesn't work, please answer in chat with a number that you can't build. So remember, I am handing you all of these building blocks from 1 to 100. I'm asking you, can you build the numbers from 1 to 100? I see we have 30 some odd people who've answered no, but I don't see... so someone's saying 1, 2, 3, 5, 7. But remember, we're only building numbers from 1 to 100. So we're not trying to build any numbers outside of 1 to 100. Oh, okay. Yeah. So what, we have so many people who've answered no. Why doesn't it work? Please don't answer in the Zoom chat, because that's not going into the poll, so. And for the record, if you're trying to get participation points, starting from today, you need to be answering in the other chat, because that's how I'll be measuring participation points. So if you ask the questions there, they will actually count, whereas the Zoom chat no longer counts. The Zoom chat's just extra now. When you say multiplicative building blocks, how are you defining it? Well, what I mean is, so for example, 2 times 2 is equal to 4. So I can build 4 from 2, from a building block that's 2. Or 2 is equal to 2, so I can build 2 out of just 2. Can't make certain numbers without divisible larger than 1. What numbers? That's the question. So when I say multiplicative building block, I just mean that you can use it and multiply copies of it, or with itself, or with other numbers in your set of building blocks to get any number. 13, 5, 7, 23. But if we're just doing numbers from 1 to 100, I have the number 17. So I have the number 17, so I can build that, because it's just equal to 17. Or it's equal to 17 times 1, if you want to actually have a multiplication in there. Well, 1 is equal to 1 times 1, or it's just equal to 1. Remember, I'm starting with these as building blocks. Anything that I start with as a building block, I obviously have. Yeah, so in this case, you can have 100 is equal to 100, or it's equal to 100 times is equal to 20 times 5. And those are both ways of building up 100 out of the numbers from 1 to 100. Okay, so given all that, let me give a couple more examples of me. So this answer here is yes, by construction, because we already have all of our numbers from 1 to 100, and so we don't have to do much building. But this next example is going to be a little bit harder. So can you build all the numbers from 1 to 100 using the numbers from 1 to 10? And if not, say why not. Okay, yes. So we have a couple people who are replying with what is going wrong. So it looks like someone has said can't build prime numbers above 10. That is correct. All prime numbers over 10 don't work. And so no, this does not work for building all numbers from 1 to 100. No, because you cannot build. So we don't know what prime numbers are. We haven't invented them yet. But yeah, so the answer someone else gave, I think that's Katie. No, because all numbers are divisible by numbers, because not all numbers are divisible by numbers from 1 to 10. So for example, can't build 11 or 13 or 17. And it's not even just prime numbers. You also can't build 22 because we only have multiplication. We don't have addition, and so you can't even build a number like 22, even though it's not prime. But we haven't defined them yet. But really, what we're just saying is that there are numbers that you can't build from just the set from 1 to 10. So the answer to this is no. Okay. So it looks like there's still some amount of confusion. So we had a lot of people who answered yes there. Hopefully that makes sense. If not, please ask me. Like this is one of the key facts about. This is one of the hard key facts about multiplication and prime numbers, and so it's really important that you understand what we're sort of going for. Basically, the goal here is if I give you a number between 1 and 100, I'm asking you, can you build it out of the set of numbers I'm giving you, 1 to 10, using just multiplication? And there are numbers like 22 that you can't. Because 22, well, that's equal to 2 times 11, but you don't have 11, and so you can't build 22. Okay, let's try again. What about all odd numbers? So is the answer to this yes or no? Okay, good. So it looked like we had someone mention that you can't build, I think that was Nirja, you can't build even numbers. Yeah, so, okay, great. No, can't build even numbers. Like 2. Or like 40, but any even number you can't build. Okay. What about if we have all odd numbers and the number 2? So this is a little bit harder, right? So like we know that it doesn't work if you don't have. Is adding just a single even number good enough, or do you need more than just one even number in order to build up all even numbers? Okay, so it looks like most people are answering yes, and the answer to this is indeed yes. And the way it works is, well, you can just divide by 2. So notice that all your numbers are divisible by 2 because they're all even. Or sorry, any odd number you already have, and so you don't need to build it. But if it's an even number, if even, divide by 2 until you get an odd number. Get odd number. Okay, so you start with like 42. Well, you divide that, so that's equal to 2 times 21, because you just divide by 2 until you get to an even number. Or sorry, until you get to an odd number. Okay, let me try one more. What about all numbers from 1 to 50 and all even numbers after the number 50? Okay. It looked like someone. So someone clearly already knows these facts about prime numbers. There you have a question mark. Yep. Let's see. We had another question in the other directly for me. Why did we divide the odd numbers? Oh, so what we did is we already had the odd numbers because that's what we were given. So the set I'm saying here is the set that we're given. So we're given the odd numbers. and the number 2. And then because we have the number 2, that means you can use 2 as one of your building blocks. And so what that means is that when you're taking an even number, you can break it up into an even number. You can break it up into 2 and another number. And you keep on doing this until you get a bunch of 2's and an odd number. And then that's one way of building it. So like 42 is an even number. You divide by 2 and that gets you an odd number. And we already have the odd number 21 in our set. Okay, so it looks like most people are answering no because someone was really clever and put in chat that there are prime numbers after 50. And that is indeed the reason here, because no, things like 53 or 59 fail. Because these numbers aren't divisible by any number smaller than, any number smaller than 50, and they're odd, and so we don't have them as starting blocks. Okay, so hopefully that gives you some sense of what we're going for. Some of you have already seen prime numbers and this is helping you, but the basic idea is, can you use multiplication? So with addition, you could build up all of the numbers from 1 to 100 just by starting with the number 1 and repeatedly adding 1. But somehow multiplication is in some ways less powerful, right? You need, even with a bunch of numbers, you aren't always necessarily able to build up all numbers from 1 to 100. So now the question is, of course, how do we find the smallest set of building blocks? How many building blocks do you need? And so, this is basically us trying to discover the prime numbers. So we haven't defined what the prime numbers are. We're going to do that in a little bit. But we're going to now try to discover these by trying to figure out what we need for the set of building blocks. So let's just try to do the numbers from 1 to 20. So we're trying to find the building blocks for all numbers from 1 to 20. Let's start with something we know works. We know that it works if we just have all numbers from 1 to 20. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so clearly this set works. Because, this is just the size of the we have all numbers. We're trying to build numbers from 1 to 20. If you start with all numbers from 1 to 20, you don't need to build anything. So now, the question is, what numbers do we need and what numbers don't we need? So I'm going to first say that the number 1, let me do this in a different color. So the number 1 is special. This is special because it's only used to make 1. Right? You notice that you don't need the number 1 ever as a multiplicative building block, because when you multiply by it, that's the multiplicative identity, and you only get whatever you started with back. Now, which of these other numbers do you need? So, do you need 20? So that's a question for chat. So someone is answering 2 and 3 are needed. No. So no, because 2 times 10 gives you 20. So no, we don't need this. This is equal to 2 times 10. So we already have 2 and 10, and so we don't need. So we don't need 20. What about, let's say, the number 19? Do we need 19? Yeah, so there's no way for us to multiply two smaller numbers together to get 19, and so we need that. But we don't need 18, because it's equal to 2 times 9. Oh, did I erase 15? That was silly. We don't need 16, because that's equal to 2 times 8. 14 is 2 times 7. 12 is 2 times 6. Well, 15, it turns out, is 3 times 5. So we also don't need that. What about 10? Do we need that yet now? Okay, so people think the answer here is no. I should be zeroing the chat so you can just... I guess it doesn't really matter. But yeah, so the answer to this is no, that's equal to 2 times 5. But then, of course, you have to be a little careful, because when you do that, you also need to make sure that you're not building this out of 2 times 10, you're building this out of 2 times 2 times 5. Because you no longer have 10 as a building block. But you can still do that, because 10 can be built from smaller blocks, and then you can build that out of And then you can build 20 out of 2 times 2 times 5 instead of 2 times 10. Let's see. 9 is 3 times 3, but then you have to change this to 2 times 3 times 3. 8 is 2 times 4, so then this has to be equal to 2 times 2 times 4. 6 is 2 times 3, so change that to 2 times 2 times 3. 4 is 2 times 2, and so this is equal to 2 times 2 times 2 times 2, and this is equal to 2 times 2. Okay? And so we're left with some collection of numbers that we can't build up from smaller numbers. So there's 2, 3, 5, 7, 11, 13, 17, 19. Okay, and there's some sense in which we're, why are we changing lows? So whenever you ask me questions in chat, please, because I might not read it immediately, please say what you're referencing. I don't actually know what you're asking when you say lows. Oh, why are we changing the ones we'd already written? Oh, that's because when we got rid of, so we first started by saying 20 was equal to 2 times 10, right? But when we got rid of 10, then all of a sudden, you can't just use 2 times 10 anymore. But you have to replace it with whatever you replaced 10 by, which was 2 times 5. So that's why you changed 2 times 10 to 2 times 2 times 5. Okay, so somehow, and this is why I was talking about this idea of discovery, is because we didn't define these numbers. These are numbers we've somehow discovered out of all possible numbers when we're trying to build everything using multiplication. What's the smallest set of numbers? So 1 is special, so we're ignoring that. So it seems as if in a set from 2 to n, the smallest set of multiplicative building blocks seems to be only numbers that can't be written as a product of 2 smaller numbers. So let's call a number composite if it is the product of 2 strictly smaller whole numbers. So you're composing it out of smaller numbers. And we'll call a number prime if it is not. So equivalently, a number is prime if it is divisible by only 1 and itself. Right? And it turns out that all numbers we discovered here, are as these basic building blocks, are numbers that are only divisible by 1 in itself. And because of that, you can't build them out of smaller pieces. Importantly, by convention, we don't consider 1 a prime. Why is that? Well, it's because 1 is not a very useful building block. So you don't need the number 1 to build any other number. And the only number you can build from 1 is itself. It's a special case, and we're not going to call it prime, even though you could define. So when we're talking about the difference between discovery and invention, well, you can define the word prime to be whatever you want, but it doesn't always make sense. And so we're going to define the word prime as a number that is divisible by only 1 in itself, but not the number 1. Okay. Any questions about all that? So we have just discovered the prime numbers. And this is sort of cool, right? So we haven't quite proven that we always get prime numbers, though. All we've proven is that, what we've shown is that we seem to get prime numbers whenever we do this. So let's go ahead and prove that the prime numbers suffice as multiplicative building blocks. So let's prove it. So clearly we have to include prime numbers, right? Because you can't build them up out of anything smaller, and so your set has to include them. So 2, 3, 5, 7, and so on. But now notice that if a number x is not in our list, then that means that you have to build it from smaller numbers in our list, right? So for example, if the number 6 is not in our list, then you have to build it from smaller numbers. So now let's let C be equal to the smallest number in our list. Well, then C has to be equal to A and B, where A and B are less than C. So for example, but A and B are either prime or they're not in our list. So for example, if you had 8, that's equal to 2 times 4. Let's say that we had a number 8, that's the smallest composite number in our list. Well, it has to be built up from smaller numbers. And so it's the smallest composite number, which means that any smaller numbers are either prime or are not in our list. So 2 is prime. and 4 is not in list. But if it's not in our list, that means that it has to be built up out of smaller numbers in our list, and so eventually we'll get to prime. So 4 is equal to 2 times 2, and these are both prime. And so because of that, we know that we can remove c, because 8 is equal to 2 times 2 times 2. And so we didn't need the number 8 in our list. So repeating, we can remove all composite numbers from our list, and we're left with just the prime numbers. And so what we've just shown is that the prime numbers not only are required to be included in our list of building blocks, they're all we need. So if you have the prime numbers, you can build everything else. With the exception of 1, but we're going to ignore 1. Okay, any questions about all that? Okay, yes, some excitement. So now, what is a prime factorization? And we're going to go into this in a bit more detail later, but the basic idea is that, well, every composite number can be written as the product of two smaller numbers. Yeah, so that's exactly what we're going to be doing now, Tiffany. The question was, so prime numbers can build any number. Yes, if you have all the prime numbers, you can build any positive number any positive whole number except for 1. So every composite number can be written as a product of two smaller numbers by definition, right? We can repeat this process until we write the composite number as a product of prime numbers, right? Because if you build it up out of two smaller composite numbers, you can just repeat that and take those two smaller composite numbers and break them up again. You're constantly dividing up these numbers into smaller building blocks. So, for example, let's say we started with the number 120. Well, that's equal to 2 times 60, right? So you're breaking up into two numbers. One of them is prime and the other one's not prime. Well, let's break up the composite number again. So then that's 2 times 2 times 30. We can break up 30 again. That's 2 times 2 times 2 times 15. And let's break up 15. That's 2 times 2 times 2 times 3 times 5. And since we're multiplying 3 times, we'll often write this as 2 to the third power, which is just 2 times 2 times 2 times 3 times 5. And hopefully it's not confusing when I use, I sometimes randomly swap between the times notation and the dot notation to be multiplication. Okay, so now we have just shown that you can take any composite number and write it as a product of prime numbers. Now, there's a very important question, if you do a different process. So notice that each time we broke up our number, we had a lot of choices in doing it. But it turns out that the choice that you make doesn't matter. So prime factorizations are unique. We're not going to prove it right now, but I'm just going to give an example. So we could have also done 120 is equal to 10 times 12, right? Well, and 10 is equal to 2 times 5, and 12 is equal to 3 times 4. And then we can break up the 4, so that's equal to 2 times 5 times 3 times 2 times 2, which, if you rearrange that, that's 2 times 2 times 2 times 3 times 5, which is still 2 cubed times 3 times 5. And so it turns out that no matter how you break things up, you'll always get the same number of building blocks, the same set of building blocks in the same numbers. Why this is the case is a little bit harder to prove, so we're going to do that later. And just for now, accept that you can build up any composite number out of prime numbers, and there is a unique way of doing it. You need the same copies of 2, you need the same number of copies of 3, you need the same number of copies of 5, and so on. Any questions about all that? Okay, great. So, let's try this out. You don't always have to reply in chat. But yes, thank you for replying in chat. It is super helpful. So, I'm going to ask you to find a prime factorization. What is the prime factorization of 720? So what you're going to have to do is you're going to have to keep on breaking it up into pieces and then figuring out what numbers go together. So I've zeroed out the chat. And just as a piece of advice, it's often easier if you break up into, so we have a couple of replies. Oh, okay, so we're getting a good mix of different things. So now, one thing to be slightly careful of. What is a prime factorization? Importantly, the question I'm asking is, what is a prime factorization made out of? A prime factorization has to be made out of prime numbers, right? Yes, the smallest combination of prime numbers. And so, is 6 a prime number? Yeah, exactly. So you can't have 6. And so I put an A to confuse you and to make sure that you're actually paying attention. So yes, that was a bamboozling. I bamboozled you by putting in 6, where A2 squared times 6 squared times 5 is 720. But it's not a prime factorization since 6 is not prime. So, well, let's solve this. I'm going to do this. 720 is equal to, let's say, 10 times 72, which is equal to 2 times 5 times 2 times 36, which is equal to 2 squared times 5 times 6 squared, which is equal to 2 squared times 5 times 2 times 3 squared, and that's equal to 2 to the 4th times 3 squared times 5. So the answer here is indeed D. Okay, so let's do another one. Let's do 722. What is the prime factorization of 722? Now, be a bit careful, because I have already demonstrated to you now that I'm a little bit tricky sometimes. Notice that if it's a prime factorization, it has to be a, well, the things have to multiply together to give 722. Okay, so it looks like many of you have taken my trick to heart, and you're like, well, it must be none of the above. Okay, and other people are saying it's B or D gets a lot of answers, which is a little bit confusing to me because we already showed that D was the prime factorization of 720. And so if you multiply D together, you end up getting 720, not 722. C, it turns out that if you multiply that out, that also doesn't get you 720. So let's actually try to solve this now. So this is equal to, well, divide by 2, that's 3 times 361. Now, the question is this a prime factorization? And the answer to that is no, because it turns out this 361 is not prime because it's 19 squared. Some of you may have recognized that as 19 squared. If you didn't, just notice that 19 times 19 is equal to, well, 20 minus 1 times 20 minus 1, which is equal to, by FOIL, 400 minus 20 minus 20 plus 1, which is equal to 361. Okay? So let's just, or you can do it the normal way. 19 times 19 is equal to 81 plus 9, which is 17, 19, which is 361. Okay? So I bamboozled you. So 361 is not prime, and so you can't use it in the prime factorization. Reminder to people in the Zoom chat, please do your votes over on the other end because I am not counting any votes over on the Zoom chat. Yes, indeed. So there are all sorts of tricks I'm doing right now. So be aware of these tricks because right now I'm deliberately making these tricks. But if you were a mathematician and you were trying to figure these out, well, you might randomly encounter these numbers and you might think you had a prime factorization when you didn't really. And it turns out that this is a problem. So much later in class, near the end of class, we'll find out that sometimes if you have prime numbers, things work much better. So as I think I mentioned in the very first day, later on we'll find that prime numbers are really, really useful for internet security. And so if you have a number that you think is prime but is not prime, it turns out that that can cause a big security hole and hackers can get into your data if you think the number is prime when it isn't. And this is a very real problem in internet security. Okay, so that goes back to this question of how do we know if a number is prime? So like 361, that's really big, right? And so like if you don't know your times tables, you might not know offhand that. Sorry, by times tables I mean the really big times tables up to like 20 or whatever. You might not know that that's not a prime number. So how do we know if a number is prime? So please put your ideas in chat. Please put them in the Bastion chat just so that you get credit for it. So does anyone have any ideas about how do you know if a number is prime? Check if it can be square rooted. Okay, so that's not a terrible idea. But what happens if I gave you a number like, let's say, 399? Divisible? Well, yeah. So it's true that it's let's see, odd and then more. Divisible by 1 or itself. It can be divided by 2 factors only. Yeah. So we're repeating the definition of how do you check if a number is prime. So okay, that's a really great idea. Divide by all numbers up to 20 or square root it. Okay, so we're starting to get to some of the other things. Try dividing by 2 or other prime numbers. Okay, so we have a lot of good ideas in chat right now. So let's start with the very simplest idea. Test if it is divisible by every number smaller than it. You just have to list all numbers smaller than C. So that's one way of doing it. That will work. So you can try dividing by all numbers smaller than it. It should be divisible by a whole number. If not, check if it's divisible by any prime number. Sounds arduous. If it can be divided by 1 in itself. Yeah, okay, so we have a lot of good answers here. So let's start with the very basic one. And so this is the one that if you don't know anything else about math, well, you can do this one. So let's do this. 361 divided by 2 is equal to 180, remainder 1. 361 divided by 3 is equal to 120, remainder 1. 361 divided by 4 is equal to 90, remainder 1. 361 divided by 5 is equal to 72, remainder 1. 361 divided by 6 is equal to 60, remainder 1. 361 divided by 7 is equal to 51, remainder 4. 361 divided by 8 is equal to 45, remainder 1. 361 divided by 9 is equal to 40, remainder 1. Don't worry, I'm not going to do this for every number, but I just want to illustrate how hard work this is. So we keep on going. 1. Oh, why did people put a lot of 1s in chat? Okay, but anyway, let's keep on going. So eventually, we're going to get there, right? So how many numbers do we have to go to before we get there? So if this number is prime, then that means we're going to keep on going until, well, we already know it's divisible by 1, but we might have to go, if the number is prime, we might have to go all the way to 359 or something. And so this is really slow, and this is kind of painful, and you shouldn't, but it will eventually get there. 15 is 24, remainder 1. Oh, I think I skipped. I think I skipped 16, but that's alright, because we know it's not divisible by 16 since it's not divisible by 2. Okay, in this case, we got lucky, right? So we got lucky because I chose a perfect square, and it turns out that 361 divided by 19 is equal to 19. Okay, well, that was not so great, right? That took a while, and it might have even been longer. I don't know if I'm right, but I realize there's yes! So there's a quick way to check if it's not divisible by any even number, by 2 and 5. Yes. Isn't that a lot to do for one question? Yes, it's way too much to do for one question. Let's try to figure out a better way of doing this. So we already have these other ideas. Another one of the ideas is to make a list of primes and test only those numbers. Because you don't have to test the number 4 if you've already tested the number 2. If it's not divisible by 2, it's not going to be divisible by 4. And so, let's see. We already have a list of primes, right? So we had a list of primes from, where were they? from when we discovered the primes. So we have a list of primes already, and so if you have a list of primes, well, you can write those down: 2, 5, 2, 3, 5, 7, 11, 13, 17, 19. Turns out the next one's 23, and so on. And so you can just try to divide by all the primes. 361 divided by 2 is equal to 180 remainder 1, divided by 3 equal to 120 remainder 1, and so on. So I already did these, so I'm not going to redo them all. And then it turns out when you get to 19, that's equal to 19. And so you have many fewer divisions, right? So, well, you don't actually have to divide by 1, because you know everything is divisible by 1. Okay, so this is still a lot of work, but it's much less work, right? Because you only have to divide by the primes, not by every number. But luckily, it turns out that, and then the other issue is then you need to have a list of all primes first. Are we sticking the numbers under 20? This will actually come up in a little bit. So I will show you why numbers under 20 are almost good enough. No, we will not be for the purpose of our class. No. Yep, 361, not 360. Yep, thank you. Yes, so no, we won't be sticking the numbers under 20. So, but now this seems really hard, right? Because I'm going to make you do all these really big numbers. And the answer is yes, but it actually gets a little bit easier though. And so I'm going to now introduce something called the sieve of Eratosthenes. So what is a sieve? Well, it's a filter. So you guys have probably seen them whenever you're cooking. You can filter stuff out. Maybe you've made pasta and you want to filter out the water and only keep the pasta. And this turns out to be a method that an ancient Greek mathematician came up with for computing all the list of primes. So the method is you repeatedly filter out multiples of the smallest remaining number in the list. So you start your filter out with multiples of 2, then multiples of 3, then multiples of 5, because 4 is filtered, so you don't have to do 4, and so on. And the sieve of Eratosthenes will then allow you to filter out all of these numbers. Okay, so let's see this in action. So I have a list of all numbers from 1 to 100. 1 is special, and then I'm left with number 2, right? So when I have the number 2, then I want to filter out everything that's divisible by 2. And I think there was someone earlier in chat, it was Rika, mentioned that there's a quick way that if a number ends in, is divisible by 2, and that's if it ends in an even number, right? So that means we're going to roll out 4, we're going to roll out 6, 8, 10, but actually the way I've written this out, you can just roll out all of these numbers. Okay, so what we've done is we've filtered out all of these numbers that are multiples of 2. Okay, so then what's the next smallest number? The next smallest number is 3. So the next smallest number is 3, and so we need to filter out all the numbers that are divisible by 3. Well, we've already filtered out 6, but we can filter it out again. So, and then 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39, 42, 45, 48. So notice that some of these numbers have already been filtered out. In fact, a lot of these numbers have already been filtered out. And as we keep on going, you'll find that more and more of your numbers have already been filtered out. 72, 75, 78, 81, 84, 87, 90, 93, 96, 99. Yes, so someone mentions charisma. Anything that adds up to 3 or any numbers that are divisible by 3. For example, 18 is equal to 1 plus 8 is 9, divisible by 3. Yes, so divisibility by 3 is also something that we know how to do pretty easily. What about divisibility by 5? Yeah, ends in 5 or 0. So we're going to start by filtering out 10, and then we're going to filter out anything that ends in 0 and anything that ends in 5. Okay? Now 7 is going to be a little bit more painful, but let's slowly do 7. So we have 7, we filtered out 14, then 21, then 28, and then 35, which has already been filtered out, and then 42, and then 49, and 56, 63. 7 is a little bit harder, unfortunately. 70, 77, 84, 91, and 98. Okay, now we have to keep on going, but what happens when you try to do 11? What numbers do you filter out when you get to 11? Well, let's see. Well, we have 11. Well, we already filtered out 22, right? And we already filtered out 33. And we already filtered out 44. Yes, you filtered out all the multiples of 11, but when you actually go to do it, well, you notice that, well, let's see. So 11, 22, but 22 is already filtered out. And 33 is already filtered out. And 44 is already filtered out. And 55 is already filtered out. And 66 is already filtered out. And 77 is already filtered out. And 88 and 99 are also already all filtered out. So we try filtering out all the multiples of 11, and we've already filtered all of them. What happens when we try to do 13? Well, when you look at 13, well, when you're filtering out, let's see, 26, that's already filtered out. 39, that's already filtered out. Let's see, 52, that's already filtered out. Let's see, plus 13, 65, that's already filtered out. Plus 13, 78, that's already filtered out. 91's already filtered out. Huh. So one of the things you should notice is that once you've gone beyond 7, like it seems like all the numbers that you're trying to filter out have already been filtered out. And so in order to use the sequence of Aristotelians on all numbers from 1 to 100, you don't actually have to do all that many filterings. You only need to filter out 2, 3, 5, and 7, and then all the rest of the numbers are primes. So now there's a question, right? So why is the sieve so fast? Please answer in chat. What is the first number that's filtered out for each prime? Okay, so 2 is the first number that's filtered. So wait, not which is the first number that you're using to filter stuff out, but what is the first number that's filtered? So, for example, let me redo this. So we 1 is special, and then we start by 2. What's the first number we filter out? We filter out 4, right? So when we have 2, we filter out 4. What happens when you are filtering? Well, let's go ahead and filter all these out again. What happens when you have 3? What is the first number that we filter out? So we're getting a little bit of disagreement here, right? But notice some people are saying 6, but we already filtered 6 out. 6 is already gone. So the first number we filter out is 9, right? So we're filtering out 9, so let me do that again. So we're filtering out all the multiples of 3, and let's see, where was that? And 3. Yeah, the 2 times multiple of it has already been canceled out. So the first one after you've already canceled stuff out. And so the answer to that is 9. Okay, so now we have 5, right? So let's say 5. What's the first number that we filter out? Well, we've already filtered out 10, 15, 20. So it's 25. So that goes to 25. And then we filter out all the remainder of these. Okay? And what about 7? Yes, so someone sees the pattern. The first number to be filtered out is indeed the square. And so the first number to filter out is this 49 here. And of course, then you filter out all the rest of them. So it turns out that when you're filtering these out, there are very few other numbers that you get to filter out. But yeah, it's 49. So we're getting the first number we filter out is the square. And this is actually something we can prove, but now we've sort of shown it like in practice, and so hopefully, so that's one of the things mathematicians do, is that you might ask these questions, but then what you do is, and you're like, well, what is the pattern here? So then the pattern we see here is that it seems to be the first number you filter out when you use a prime as the filter is its square. So this gets us the properties of the sieve. When any number is filtered out, obviously all of its multiples are also filtered out. So, for example, 4 is filtered out for the prime 2. But then, of course, all multiples of 4 are also filtered out, are also filtered, because 4n is equal to 2 times 2n. Okay, so that was one of the obvious parts. The next part, the first prime p to be filtered out is always p squared. Because if you had any smaller multiple p times n, where n is less than p, that would have been filtered out when, not that, sorry, why did I write a? When n was filtered out. When n was filtered out. So for example, if you had 11, 22, 33, 44, 55, 66, 77, these are all the multiples, right? And one of the things you'll notice is that this is filtered out with 2. This is filtered out with 3. That's filtered out with 4, 5, 6, 7, 8, 9. So those are all filtered out when some smaller number was filtered out. And therefore, the first number to be filtered out when you have a prime that hasn't already been filtered out is going to be that prime squared. Unless to figure out if the number is prime, you only have to run the sieve of Eratosthenes up to a prime that's less than or equal to the square root. And if n is not prime, then it must be divisible by some prime p that's less than or equal to the square root. And so, what do we mean by that? We mean that if n is equal to ab, so either a is less than or equal to root n, or b is less than or equal to root n. Okay, so that means that in order to get figure out if a number, say 400, is prime, well, I mean, it's pretty obvious that it's not prime, but you only need to check the numbers up to 200. You only need to check the numbers up to its square root. You only need to check the primes up to the square root. So in theory, with list of primes, so we do have all the primes now. So in this case, they were 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97. So with this list of primes, oh sorry, I didn't mean 20, yes, not 200. Yeah, so with this list of primes, you can in theory check if any number is prime up to 10,000. Oh, you thought it was only till 7. So we only needed to check till 7 to figure out, or only needed to check until 10, really. Like, the real answer is you need to check until 10 in order to get all the prime numbers between 1 and 100. But now if you want to get all the numbers between 1 and 10,000, you only need to check this list of primes here to check to see if any number between 1 and 10,000 is prime. Okay, let's try that out. Oh, I am running late on the break. Give me a moment and I will give you a break, and I think we might run out of time today, but that's alright. So, where were we? So we had some various properties of the sieve of Eratosthenes. So, what are the primes between 210 and 220? So how do we figure this out? Well, you know that if you're looking at the primes between 210 and 220, so let's list those out, you only need to check the primes up to the square root. So you only need to check primes up to, well, notice that 17 times 17 is equal to 289. And so you don't need to check up to 17. So primes 2, 3, 5, 7, 11, 13, 17, but you don't need to worry about 17 because 17 squared is bigger than 220. So you only need to check this set of primes, 1, 2, 3, 4, 5, 6, and then you'll know if all numbers between 210 and 220 are prime. Okay, looks like someone's already found the answer, but yes. Well, let's follow it through. So, what numbers are divisible by 2? Well, 210, 212, 214, 216, 218, 220, and therefore those numbers aren't prime. What numbers are divisible by 3? Well, someone else gave a rule for divisibility by 3, just add up the digits, and it turns out 210 is also divisible by 3, and then you can just add by 3 each time to get the next number divisible by 3. Did I do that right? Oh no, I did not do that right. I clearly can't do the addition. So that one, 219 is the one that's divisible by 3. So 219 is divisible by 3, and so therefore, that's not prime. So what numbers are divisible by 5? Well, divisible by 5, you have 210, 215, and 220. What numbers are divisible by 7? Well, 7's a little bit harder, but we can do this division. So let's say we do divide by 7, and what you end up with is, it turns out 210 is divisible by 7, and then you also have 1, 2, 3, 4, 5, 6, 7. 217 is also divisible by 7. And what else? So let's see, what's divisible by 11? It turns out 218 is divisible by 11, but we've already gotten rid of that one. And then you check the 13. Oh wait, sorry, I did that wrong. 11 was, sorry, I'm not actually doing all these divisions on the fly. I have them written down already. So that was actually 13. That was divisible by 218. And then for 7, let's put a different symbol in. So, sorry, for 11, let's see, which of these are divisible by 11? 220 is divisible by 11 and nothing else. And so all we're left with at the end of the day is 211. Every other number is divisible by one of the numbers between, one of the prime numbers between 1 and 17. And we only had, yes, 211 is prime. So this is prime. So we only had to check a few prime numbers to figure out whether or not 211 was prime, and that all these other numbers weren't prime. And so that is the power of the sieve. 13 is crossed out. Is 13 crossed out? Yes, 13 is crossed out. Oh, sorry. What I've been doing is I've been crossing out the numbers. So we need to check the numbers up through 13. 213 is crossed out. Yeah. So all these numbers are crossed out except for 211. Okay, so that is the power of doing the sort of testing, is that you only need to test up to the square root of the number, and then you're done. Okay, so let's have y'all try this out. I've given you a list of the primes up through 30, up through 31, and then my question is this a prime number, a composite number, or both, or neither? Let's start off easy. What is 1? Is it the prime number, is it the composite number, both, or neither? Okay, so the answer to the list is we're going to call, oh wait, that do it as something, okay. We're going to call this neither. Then that's by convention. Just because it's not a useful building block. So yes, it is divisible by only 1 in itself, and so you could make the argument that it should be called prime, but it's just not useful for us to call it prime, and so we don't. Okay, what about, come on, what's going on? What about 87? So people are guessing, okay. So people are guessing either B or D. Note, of course, that for any positive whole number, only one is neither. Everything else has to be either prime or composite. Yes, divisible by 3, right. So 87 divided by 3 is equal to 29. You can also see this because 8 plus 7 is also divisible by 3. So that's a quick check for divisibility by 3. So that is composite. Okay. Oh, wrong way. What about 97? Is this prime? Notice that we already computed all the primes between 1 and 100, so if you want, you can just go back to checking over there. And the answer is, well, if you look back over here, 97 is on our list, and so therefore it is prime. And so we already did that one. So that one is prime. Okay, let's do a slightly harder one. 359. Is this one prime? What do you have to check? Oh, I did not reset, but that's alright. We'll just keep on going on this one. Okay, so we have a lot of people who are answering that it is prime, and that is correct. And in order to do that, you just have to check 2, 3, 5, 7, 11, 13, and 17. You don't have to check 19 because it's over the square root, so you have to check each of these. Check each of these. Okay, what about 401? Is this prime? So you do have to check all these again, but you do end up with this is prime. And so you have to check through 19. And for the last one, let's do 623. Is this one prime? Oh, let's see, this is 87 is composite. Yes, someone found it. So this is divisible by 7. Yep. So it turns out that if you take 623 and divide it by 7, you end up with 89. So this is composite. Okay. Yeah. Okie dokie. So hopefully, I think that is the end of the first half of lecture. So thank you all so much. And we are going to take our break now. So let's go ahead and take a... Oh, I ran super late on this. Well, I should give you your 10-minute break. So be back at 10:33, and then we'll have a very short, last portion of class.